Okay, hi Year 11. Today what we're going to be having a look at is exercise 17C in extension, and it's graphs involving inverse trig functions. So I've split this up into two videos, I think I will, and we'll have a look at the graphs first and then we'll have a look at some of the proofs in a moment. So the first thing here says to sketch the following graphs stating the domain, range and asymptotes if applicable. So we have a look at the first one. A, we've got y is equal to sine inverse of x plus 1. So the same rules are going to apply here as when we did our transformations in advanced. When we're adding 1 inside the brackets, we're moving the curve 1 unit to the left. So the way I'd probably do this is to, if you can do it straight up, that's great. I'd generally sketch a graph of inverse sine of x and have a look at what the domain and range are and then move that across 1. So let's do that. Okay, so the dotted line down below here is my inverse sine of x curve. So the domain is between -1 and 1 and our range is between minus pi on 2 and pi on 2. We're going to move that graph 1 unit to the left. So instead of cutting at the origin, I'm going to cut at this point here at -1 on the axis. And everything's just going to move 1 unit across. So my new curve is going to look like this. So I'll better write what the curve is. So it's inverse sine of x plus 1 is going to have a domain of, we're between -2 and 0 now. So everything's moved across 1 unit. And our range, however, it hasn't shuffled up or down. So our range is going to be between minus pi on 2 and pi on 2. We have a look at the second one. We've got y minus pi on 2 is equal to inverse tan of x plus 1. So like the sine inverse we just did, we're going to be moving our tan 1 unit to the left. But we've got this pi on 2, and what I would do would be getting this pi on 2 and moving it to the right-hand side. So we have plus pi on 2, which means we're going to be using that to move our graph pi on 2 units upwards. So popping that over there, it's just like we did in advance with our transformations. So if you can do that, draw it straight up. But what I'm going to do is I'm just going to draw my straight out tan inverse of x, sketch that one, and then draw the other graph over the top of that. So I've just quickly sketched my inverse tan of x curve here. And this is something that you could do in your exam papers if you like. If you bring a pencil in and sketch that base curve on your paper and you've got your pen to draw your accurate one over the top, because you're still going to need to know how to sketch these. It's great to pop it into Desmos, but Desmos isn't there for you in an exam, so you need to have a look at being able to do that without Desmos. So first of all, let's shift this graph 1 unit to the left. Going to be my final graph because I still have to move it up. So 1 unit to the left would have the same asymptotes. It's just shuffled that graph along there. Now, if I want to add my pi on 2, what that's going to do is it's going to shuffle this bottom asymptote at minus pi on 2 down here up to become the x-axis. So I'm going to have an asymptote along the x-axis. I'm going to have this point 1. It's going to be up here. And my next asymptote, actually we might put that up in a second, it's going to be up higher, isn't it? I'm going to have pi on 2 plus another pi on 2, which means pi. So I'm going to have pi up here as my other asymptote. Oops, not pi on 2. Draw this graph in now. It's going to move up here. It's the bold one. So if you did it like this in an examination, you would be making sure that this final graph was done in pen. And that's what that looks like. Now let's have a look at our domain and our range for this function here that we've got. Okay, so what we're going to have is, if you have a look at your x values, our domain, we can have all real values of x. And our range, our y values, well, we've got asymptotes along the x-axis at y equals 0, and we've got asymptotes at pi, so we're going to have 0 is less than y is going to be less than pi, and that's our function drawn. Okay, so if you need to pause the video now and go back and have a look at the exercises that relate to drawing those graphs, now would be a good time to do that. But I think I'm going to just continue the video on. We want to have a look at some proofs. Now, a lot of you like to do proofs your own way. I want you to do the proof the same way as I'm going to do it in here. When I do a proof, I can't assume that I know what's happening in my question. I'm going to start on my left-hand side and I'm going to hopefully prove or move algebraically to my right-hand side. And that's what I want to do below here. So it's saying that y is equal to sine inverse of x and that it is odd. And we want to show that this left-hand side, sine inverse of x of minus 1 is equal to minus sine inverse of x. Now, we know it's odd. Let's go back and have a look at a diagram of sine inverse of x. Okay, so here's sine inverse of x in our restricted domains and ranges. And if you have a look, if we were to take that top part of the graph and flip it around the origin, it'd be the same as our bottom half. Like a cubic, basically, y equals x cubed. That's what's happening here. So that is an odd function. And the test that we've been doing in advanced maths for odd functions, we could say that f of minus x is equal to minus f of x. If that's the case, then it's odd. And that's all we're doing here, is saying that our function of minus x is equal to minus of our function. But we're going to prove it. So we're going to start with our left-hand side. And we're going to say our left-hand side is equal to sine inverse of minus x. And I'm going to let y be equal to sine inverse of minus x. Now we can also write this as sine of y is equal to minus x, but we've got to remember that we are in a restricted domain here, so we're between minus pi on 2 and pi on 2 for this to occur. If I divide both sides by this minus 1, I can say that minus sine of y is equal to x, and I might just neaten that up by writing it as x is minus sine of y, because I always like to have the main unknown on the left-hand side. So I'm going to figure out what this is actually meaning. X is equal to minus sine of y. I'm going to pop an all stations to central up here. And we've got our y here being between minus pi on 2 and pi on 2. So we've got pi on 2 up here and minus pi on 2. So we're basically working in those two quadrants there. And we want minus sine. Where is sine minus in those two quadrants? It's down in that quadrant over here, in the fourth quadrant. So what happens in this quadrant here is we would be looking at minus y. Okay, so if y is our angle in the first quadrant, in this angle it's going to become minus y. So x is going to be equal to sine of minus y. I can also write this as sine inverse of x is equal to minus y. And if I divide both sides there by minus 1, I'm going to be equaling what I got my right-hand side to be up here. So therefore, minus sine inverse of x is equal to y, and that's our right-hand side. Okay, so let's have a look at the next proof. The next proof is doing the same, but we're doing it for tan. Okay, so you can pause the video to have a look at that tan proof, but it's exactly the same as the sine proof. It's just got tan in there. Let's have a look at the next one. Now, we talked a little bit about this in the last lesson. It says y is cos inverse of x has an odd symmetry about the y-intercept. Okay, so we looked at sine and tan inverse being odd, and a definition of an odd function is that it is mirroring or rotating around that 0, 0 origin point. This is happening with this curve, y equals cos inverse of x, but it's happening around the point 0 pi on 2, or where it cuts the y-axis, so it's a little bit different. So therefore what we can show is that cos inverse of minus x is equal to pi minus cos inverse of x, and it falls out fairly simple. Instead of working in that first and fourth quadrant, we're going to be working in the first and second quadrant, and that's where that pi is going to come into play. Okay, let's have a look. Let's go left-hand side. So the left-hand side is cos inverse of minus x. So we are over here. Okay, we want to work that through so that we can end up with this right-hand side here. So let's see how we go. So I'm going to let y be equal to cos inverse of minus x. I can also write that as cos of y is equal to minus x. And remember that with our restricted domain and ranges in here, our restricted range is 0 and pi is what our y is between. Okay, so if I divide both sides of my equation now by minus 1, I'm going to get minus cos of y is equal to x. And I'm just going to write that as x is equal to minus cos of y, because that's how I like to write it. You don't need to write like that if you don't want to. This is what I've got. Now, what I need to think of is, where is x having this happen? So let's look at our all stations to central now. So we're over here. All stations to central. We are working in this domain. So we're in that first and second quadrant. And where is cos negative? Cos is negative over here. Okay, because only sine is positive in that quadrant. And what happens in that quadrant? Okay, if we've got our angle of theta in this first quadrant, in the second quadrant, what happens? It's going to be pi minus theta. And that's what we want to have work through the rest of the proof. Okay, our angle though we got is y. So in the second quadrant, instead of having minus cos of y, x is going to be equal to cos of pi minus y. Okay, so if you're stuck here, you're going to be thinking, well, where do I need to go? I need to be thinking about the inverse, and I need to get the pi out of my brackets here. So what I'm going to say is that cos inverse of x is going to equal to pi minus y. We're nearly there. I am going to write that also as y is equal to pi minus cos inverse of x. Let's have a look back at our question, which is what we wanted, which is our right-hand side. So there's that proof done. Lucky last, this one's a little bit harder, and that will lead us on to the next part. Okay. Complementary angles, inverse sine of x, plus inverse cos of x is pi on 2 between x, or a range of minus 1 to 1. So what you've got drawn down here are our inverse sine curve, which is this one, and our inverse cos curve. Let's look at it graphically to start with. So if we think what we do when we look at that graphically, if we add coordinates of the inverse sine to coordinates of the inverse cos, it should equal pi on 2. So let's have a look at the right-hand side here. 1 at the point 1, which is 0. 0 plus pi on 2 gives me a pi on 2 value at that point. Let's move over to here where it's crossing. We've got pi on 4 and pi on 4 for both graphs. If we add pi on 4 plus pi on 4, we get pi on 2. So you can see where it's happening, what's happening here. We've got 0 plus pi on 2 over here, which is pi on 2. Okay, and point over here, we've got pi plus minus pi on 2, which is also pi on 2. So graphically, you can see when we add all the coordinates of that inverse x curve, sine curve, and inverse cos curve, we're going to get pi on 2. Okay, let's see if we can get this to work algebraically now. So I am looking at, I'm not going to work left-hand side to right-hand side. I'm going to look at the cos inverse of x first. So if we just let alpha be equal to cos inverse of x, then I can say that cos of alpha is equal to x. But we're looking in this case that alpha is going to be between 0 and pi in our restricted domain. Now we need to relate sine and cosine back with each other. And we need to think about what happens when we're working just in an old-fashioned right-angle triangle. The angles of sine of alpha and cos of alpha are going to be complementary, or adding to 90 degrees. So what we can say then is that sine of pi on 2 minus alpha is also equal to x, because this cos of alpha is equal to the sine pi on 2 of alpha. And if you want to have a look back at a very simple basic right angle triangle, you can see how that would work, and I might show you that in class. Okay, so let's just neaten up our sine here. So I can write So I can write this as sine inverse of x is equal to pi on 2 minus alpha. And that sine inverse of x plus alpha is equal to pi on 2. And we're basically saying in here that we're back into sine. Remember, sine inverse is restricted, and that's between minus pi on 2 is less than or equal to our x, which is pi on 2 minus alpha, and pi on 2. But we know this is the case because we're always working in those restricted domains. So sine inverse of x plus alpha is equal to pi on 2. And we know right from the start, and I'll just highlight that for us, that this alpha here is also equal to this alpha up here. So that basically means that sine inverse of x plus cos inverse of x, which is what our top alpha here, we've said it is equal to pi on 2 as requested.